Early AI agents operate on synchronous blocking loops. They send a request to a server, and the entire system freezes while waiting for a response. On a desktop, this linear execution creates a sluggish experience. The agent remains blind to real-time state changes on the local machine until that single network request resolves. Goose, an open-source framework developed by Block, solves this latency problem by building the agent entirely in Rust. This diagram illustrates the difference. On the left, a standard script stalls at the network request. On the right, Goose uses an asynchronous evaluation loop. The loop spins continuously, spawning network requests as parallel background tasks without ever pausing the core execution. We are going to build this architecture layer by layer from first principles to understand how it works. To survive as a long-running process on a local operating system, the framework has to solve 4 distinct engineering challenges: concurrency, extensible tooling, local security, and memory exhaustion. An LLM is inherently non-deterministic. Achieving true local autonomy requires wrapping that model in a strict, highly concurrent software architecture. Goose's foundation is the agent struct. It houses a continuous evaluation loop, utilizing a Rust-based async actor model. The Tokio runtime handles the heavy lifting, executing hundreds of background tasks concurrently while keeping the main event loop unobstructed. To maintain stability across parallel processes, Goose relies on immutable data structures. When shared mutable state is required, it's strictly controlled through synchronization primitives. However, this specific design introduces a new routing problem. The constantly processing loop needs a way to handle sudden user inputs. The solution is the multi-turn scheduler, where incoming inputs stack in a priority queue. This queue evaluates real-time priority, preempting or queuing tasks. When requiring an LLM, a provider router branches to interchangeable endpoints like OpenAI, Anthropic, or local Llama. If multiple providers are configured, dynamic load balancing routes requests based on strict token limits or latency thresholds. Combining a Rust actor model with a priority-based scheduler guarantees the agent remains instantly responsive. This architecture completely masks external network lag behind local asynchronous processing. Early agents hard-coded capabilities directly into the application layer. Adding a new tool required rewriting the framework itself. Goose bypasses this limitation by adopting the Model Context Protocol, or MCP, a standardized specification for tool discovery. Goose operates as an MCP client. The agent dynamically connects to external MCP servers, ingesting raw capabilities and translating them into uniform Rust structs. Supplying dozens of granular tools drives up token costs. To fix this, individual tool blocks like search, scrape, and summarize merge into one larger encapsulated skill. Executing a skill consolidates complex operations. It can search the web, scrape a specific page, and summarize the contents without requiring 3 separate round trips to the LLM. Standardizing on MCP instead of native integrations allows for massive horizontal scaling. The agent's capabilities expand infinitely without requiring a single update to the core framework. Deploying an agent directly onto a desktop introduces extreme risk. The system has deep, active access to the user's local file system. To mitigate the threat of malicious tool outputs, Goose enforces a robust dual-layer security model. The first layer isolates execution. When a tool runs, it operates inside a restricted container via Docker or a lightweight WebAssembly runtime. This sandboxing ensures that even processing malicious data leaves no pathway back to the host operating system. The second layer deals with intentional yet dangerous actions. Sandboxing can't stop an LLM from deciding to delete a directory. For these operations, a human-in-the-loop checkpoint halts the destructive path completely until manual approval. Because of the Tokio runtime, this pause is handled entirely asynchronously. The state freezes securely to wait for the user prompt without blocking the UI or timing out. The combination of strict WASM sandboxing and required HITL checkpoints makes local agent deployment fully viable for secure enterprise environments. Long-running agents collide with a mathematical limit, the finite context window. Once the memory buffer fills with tokens, the process crashes. Goose manages this ceiling through active context compaction. When nearing capacity, verbatim text is discarded, compressing older messages down into dense semantic nodes. On long-running sessions, this compaction strategy reduces token usage by 40%, keeping the payload below limits. However, summarizing historical data introduces a secondary risk. Over thousands of turns, small deviations compound into massive hallucinations. To prevent structural drift, Goose employs memory verification. It periodically pauses to cross-reference internal memory against the file system, verifying files still exist and match internal summaries. Context compaction keeps the model running. Strict verification ensures the agent remains grounded in reality, running stably for days at a time. This diagram illustrates the completed architecture. A priority queue feeds the actor loop, routes to load-balanced providers, executes sandboxed MCP tools, and stores results in a verified, compacted memory buffer. User commands traverse this pipeline, executing in milliseconds. The LLM provides the raw reasoning engine, but the rigid software scaffolding dictates how effectively that engine can interface with a local environment. Concurrency and speed are handled by the Tokio Actor Model and priority queue. Safety and longevity are enforced by WASM, HITL, and context compaction. This precise, deterministic framework operates flawlessly at high speeds, standing in stark contrast to the synchronous blocking scripts used in early AI experimentation. Building autonomous systems requires looking past prompt engineering. It requires architecting strict, high-performance software bounds around non-deterministic models.